As you're watching this video, you're experiencing something that didn't have an accurate scientific definition until the middle of the 20th century. If you look down at how long this video is, you can see it. The seconds are ticking by. The unit of time we all know and probably give it barely a second thought. The unit of time GPS signals, phone calls, and financial transactions depend on. We didn't have a definition for the second that was independent from the rotation of the Earth for the longest time. But one element allowed us to define the second in a cosmically objective manner. That element is cesium. Hello and welcome to Meet the Elements, the series where I take a look at the stories of humanity through the lens of the periodic table. Today's focus is on cesium, and on paper it looks like a lot of other metals. It sits towards the bottom of group 1 on the periodic table, the same group as sodium and potassium. But digging into cesium's story reveals some really interesting ways cesium has impacted human history. And it was discovered, of all places, in a glass of water. So let's start there. But first, make sure you subscribe and hit that notification bell if you don't want to miss upcoming episodes of Meet the Elements. And now that you've done that, let's take a look at cesium. The year is 1860, and we turn our attention to two scientists, a chemist named Robert Bunsen and a physicist named Gustav Kirchhoff. The pair had been experimenting with using light as a way to interrogate matter. Now, Bunsen you might recognize. He's the one who invented the Bunsen burner, but Bunsen's burner was really more of a footnote in his career to what he and Kirchhoff developed together. The idea is pretty simple. When you heat an element in a flame, like the flame of a Bunsen burner, it emits light, and it emits light of specific colors at specific wavelengths, like a sort of atomic fingerprint made of light. And you've probably seen this chemistry demonstration at some point. Sodium burns with a yellow flame, lithium burns red, potassium gives off a pinkish-purple hue. Each element has its own signature glow. Bunsen and Kirchhoff took this concept and used it to build a device called a spectroscope, an instrument that could spread that emitted light out into its component wavelengths. It uses a prism to split the light the same way it splits sunlight into a rainbow. And suddenly, these colored flames were infinitely more useful. They were readable. This was the birth of flame spectroscopy, and it meant you could identify an element without needing to isolate its pure form. You burn it, read the spectrum, and match the pattern. And in 1860, Bunsen and Kirchhoff decided to analyze a sample of mineral water from Durkheim, a location in what is now southwestern Germany. They evaporated tens of thousands of liters of this mineral water to a concentrated residue and ran this through their spectroscope. They found potassium, lithium, sodium, all expected. But then there were two bright blue lines they had never seen before. It didn't fit anything they had on record, so they knew it had to be a new element. They named the element cesium from the Latin word caesius, meaning sky blue or bluish-gray. Cesium was the first element to be discovered by spectroscope, the new analytical tool that let them read matter at a resolution that no microscope could touch, a pattern of light and information. Now, pure cesium as a physical metal is pretty neat. It's incredibly soft, like most of the other Group 1 metals, it has a golden sheen to it, and its melting point is just about 28 degrees Celsius, just above room temperature. On a warm day, cesium could melt in your hand. But don't test that, because cesium reacts violently with water, like it will literally explode type violent. But what Bunsen and Kirchhoff found would sit relatively unused for the better part of the next century, until we needed to find a better way to keep time. For most of human history, a second was just 1/86,400th of a day. You take a day, divide it into 24 hours, divide each hour into 60 minutes, and each minute into 60 seconds. Simple arithmetic. But here's the thing. The Earth doesn't actually rotate like a giant clock. It's gradually slowing down over geological time, and its path around the sun isn't perfect either. The day itself is not a perfectly reliable unit, not at the level of precision that modern science requires. There were inconsistencies with how we measured time. Metrologists, the scientists who study measurements, would slip in a leap second every few years. By the mid-20th century, when the scientific community was working to standardize units, we needed a better way to define a second. And that's where cesium comes into play. Cesium-133, the only stable isotope of cesium, has a very specific quantum mechanical property. When exposed to microwave radiation at the right frequency, cesium's lone outermost electron jumps between two closely spaced energy states. It oscillates. And that oscillation is, as far as we can determine, perfectly consistent. It doesn't vary with temperature, pressure, or the wobble of a planet. It's baked into the nature of the atom itself. In 1967, the International System of Units made it official. 1 second is defined as exactly 9,192,631,770 of those hyperfine transitions in cesium-133, a fixed definition of a second that doesn't rely on rough approximations. And that number was chosen to match the old astronomical second as closely as possible. Scientists didn't want to change time, they were just trying to find a better way to measure it. And cesium atoms are used in atomic clocks to this very day, keeping time to within 1/3 millionth of a second per year. They keep time by measuring the number of photons that those hyperfine transitions emit. And those atomic clocks allow for accurate timekeeping across the entire planet. Your phone or computer gets signals from atomic clocks to keep its own clock accurate. Financial markets run on this atomic time. Air traffic control, global communications, all of it synchronized to the quantum oscillations of cesium. But not all cesium is cesium-133. On April 26, 1986, reactor number 4 at the Chernobyl nuclear power plant in what is now Ukraine experienced a catastrophic failure. What followed was the largest uncontrolled radioactive release in human history. And one of the primary contaminants released into the environment was cesium-137. This isotope of cesium isn't natural. It's a fission product created inside a nuclear reactor. It's unstable, radioactive, and persistent. Cesium-137 has a half-life of roughly 30 years. Here's what that means in practice. 30 years after Chernobyl, so 2016, about half of the cesium-137 released was still present in the environment. A massive portion of Europe received cesium-137 contamination above detectable thresholds. But the fallout reached well beyond Ukraine, spreading into Belarus, Russia, and across parts of Western Europe, even reaching as far as Ireland. Now, what makes cesium-137 particularly dangerous from a biological standpoint has to do with its chemistry. Cesium is a group 1 element, an alkali metal. In the body, it behaves similar to potassium, but your body doesn't distinguish potassium and cesium particularly well. Potassium is essential to your cells, so when cesium-137 enters the body through contaminated food, as one example, the body treats it like potassium. It distributes through the body rather than concentrating in one location, and as it sits there, it irradiates you from the inside. And that's the problem scientists and health workers faced in the years and decades following Chernobyl. Chronic, low-level irradiation of populations from an element chemically masquerading as something essential. Chernobyl became, among many other things, the world's largest and most tragic experiment in long-term, low-dose radiation exposure, and cesium-137 is the contaminant still ticking in the soil today. So that's cesium, element number 55. It was discovered in mineral water by 2 scientists pioneering the chemical language of light, and then it was pressed into service as the atomic heartbeat of civilization, defining our every second by quantum oscillations, and carrying in a different isotope one of the darker chapters in the history of nuclear energy. That's the thing about elements. There's hardly ever just one story. The same group 1 chemistry that makes cesium-133 the most precise clock in the world is the same chemistry that makes cesium-137 behave like potassium in your muscles. Same element, same atomic identity, 2 completely different faces. Thanks for watching. I love the idea of quantum oscillations in a cesium atom being used to define how long a second is. But what about you? Do you have a favorite fact about atomic clocks, or maybe you have something about Chernobyl's legacy that you want to share? Leave a comment and let me know. I'd also like to thank this commenter for suggesting I take a look at cesium. If you have an element you want me to cover, make sure to leave it in the comments. And if you want to hear more stories hidden within the periodic table, make sure you subscribe and hit that notification bell so you don't miss the next episode of Meet the Elements.